My name is Sean Bentley. I've been with GoEngineer and with SOLIDWORKS in general since 2006. I'm here today to try to share with you the general analysis principles of SOLIDWORKS static analysis. On the agenda for this presentation, I plan on starting off with a quick overview of the analysis packages. If you've seen any of my presentations before, you've probably already seen some of these slides, but just bear with me, and then we'll get to a little bit more of the heart of the content, where we'll really start talking about the differences between SimXpress static analysis and nonlinear analysis. So we'll really have to talk a bit about what is nonlinear and what's the meaning of these words linear versus nonlinear to really get into the weeds. And I'll show you a batch of different animations to try to help clarify some of those ideas to you. And then finally we'll go through a more specific application where we'll run several different types of analysis, SimXpress, static analysis, and nonlinear, to try to solve virtually the same problem. And you'll see some of the assumptions that I'll be forced to make along the way depending on which level tool that I have access to. So each of these tools is able to solve this type of problem I'm about to present, but it's just some of the assumptions and errors that you'll be introducing. We'll see some of those differences. So there's going to be the three main points here. So let's start off though with a little bit of a background on some of the packages. As some of you might already be aware, SOLIDWORKS Standard and Professional comes with these two tools, SimXpress and Basic Motions. Now the SimXpress tool is fairly limited, allows you to do single body part analysis only. More on that in a moment. SOLIDWORKS Premium expands those two capabilities. You can kind of see the expansion going from standard to premium here. It expands those two capabilities to allow you to do full-blown static analysis for assemblies and also time-based motion analysis. And then further than that is the SOLIDWORKS Simulation packages, which you again see further expand the analysis capabilities. We have Sim Standard, which is, you can kind of tell it's pretty similar to SOLIDWORKS Premium, has a few extra tools on top. Simulation Professional, the key tools there for vibration frequency analysis and for thermal analysis as well. And then the Sim Premium, which we'll be getting into a little bit in this session here, the nonlinear specifically. So what I plan on covering is just a subset of these tools, right? The SimXpress, the static analysis for assemblies, and also nonlinear static. So virtually this chain of structural static analyses. So let me lay out then the difference between these tools a little more clearly, give you the quick summary of it. Basically, the SimXpress, here's some of its limitations. I'm not going to read through the whole list here, but it just gives you a sense of single body, you can only fully fix faces, that kind of thing. The static analysis tool has fewer limitations. You'll be forced to make fewer assumptions with this tool, but it still does have some limitations when compared to its counterpart nonlinear. For example, linear material only, no, you can't do load sequencing, just to name a few. Now really, if I had to paraphrase this down to like just a few words, it kind of boils down to this. SimXpress is purely a linear study. Static analysis for assembly is partially nonlinear, and then nonlinear analysis, sort of full-blown nonlinear. So we do need to be clear about this word linear. What do we mean by this word in the context of structural analysis? So in a lot of training classes that I teach, I often ask this question, and sometimes I get answers that usually something like maybe constant load. Is that what it means? Kinda, but there's more to it than that. Does it mean single load a load in a single direction? You're probably thinking a little more like flow express or something there. That's not exactly what we're talking about. Really, the meat of it, what we really mean when we say linear is we mean your loads are proportional to your displacements. Now, let me unpack that a little bit, and that's this first chunk of this presentation is going to try to help unpack this. But what this boils down to is if you apply a load, some load level here, on your model, you're going to get a displacement. Okay. And if you apply any other load magnitude, it's going to fall along this line, this proportionality line. In other words, if you double the load, you'll double the displacement. You cut the load in half, you'll cut the displacement in half. That's what we mean when we say study is linear. We mean that there's this relationship and all sorts of other proportionalities come along with it. So when do we break this linear concept? That's what we'll be getting into next. So when we want to run static analysis on assemblies, this is where we need to have access to some nonlinear tools. Okay, so there's three different categories of nonlinearity that we might want to draw from. One of them is we'd love to have contact for assemblies. It's really important. So we need to introduce some contact nonlinearity. Also potentially some geometric nonlinearity. I'll show you some animations to make this a little more clear. And as well, maybe you'd like to account for material nonlinearity. Okay. So what do we make of these? So as far as contact nonlinearity goes, here's what we're talking about, this type of thing. So if you have a contact set up in your study, we have sliding contacts, no penetration, shrink fit, and virtual wall. All three of these contact types are nonlinear contacts, and they're available to you in static studies for assemblies. Why are these nonlinear? Well, you can kind of see this in animation I'm showing. Is the force proportional to the displacement? Truly, it's not exactly proportional. So just by the nature of there being the kink in this curve makes this a nonlinear study, and it's going to inherit all the attributes of nonlinear studies, such as longer run times, iterative solving, where we're running it in small load steps and incrementally increasing the load. It's going to inherit all those properties. So this is probably for some of you, you might have noticed as soon as you turn on some no penetration contact, all of a sudden it takes your study a lot longer to run. This is why it's now a nonlinear study. Now, what about this other type of nonlinearity, geometric nonlinearity? This one's a little harder to really drive home the point. It's a little more abstract. So let me show you some animations to maybe a few examples might just help to clarify it without having to get too deep into the weeds. So the basic animations I'll show you in a moment. I'm going to demonstrate a linear study which uses straight line deformations where we can't have large rotation and where we assume constant geometric stiffness. I'll show you animations of each one of these three key points here. Versus nonlinear, we can have curved deformations and large rotations and so on. So let's look at the first point, straight line deformations. So I've got this simple beam here. Think of it as like a hose clamp, because what I'm going to do is I've got the left end fixed, and the right end I'm applying a twisting load to it, twisting it around. So what I want to see happen is I want to see this thing get twisted all the way around, maybe come all the way back here and touch this like a hose clamp. Okay, if I run this inside of a linear solver, this is the response I get. Okay. See, applying that twisting load, it doesn't really twist it all the way around and connect it to there. You see the deformation, we have what we call straight line deformations. If you follow any given point with your eyes, it moves in a perfectly straight line. Okay, versus if we run nonlinear, so that's incorrect. So if we run nonlinear though, if we run it as sort of a nonlinear or include some geometric nonlinearity into our study, we can account for this. Okay. Another sample, one that you've probably seen if you've run a few static studies of your own, you've probably seen this behavior if you have something that's spinning or rotating a little bit and it kind of looks like it grows. It's because in a linear study, large rotation is prohibited. It kind of boils down to that straight line deformation thing again, actually. It's the same kind of thing, just a different application of it. Versus nonlinear, okay, you can have large rotations. You just kind of see this thing twisting rather than it kind of. So as long as the deformations are small, we can assume it's a straight line. Okay, but as soon as they get big, we start to deviate a little bit. You know, here the results would match if the rotation was only a couple degrees, but as soon as it gets up to like 180 degrees or something, it's way off there. And then finally, one third one, and this is really more fundamentally what it boils down to, what geometric nonlinearity boils down to, is constant geometric stiffness. And probably the best, simplest example I can give you of this is if we look at any kind of thin plate or thin membrane, if you think of putting a pressure on it, think of like a milk jug, milk container, you know, you fill it up and the walls get sort of stiffer. Trampoline sort of develops a membrane stiffness when you push on it enough. So this membrane stiffness, though, isn't present initially. So if you run this as a linear problem, it way overestimates the displacements versus if you run it as nonlinear, include some changing geometric stiffness. I get it's able to develop some of that membrane stiffness over time. And here you can kind of see the graph of those two. The linear assumption way overestimates the displacement, whereas the nonlinear, it knows to update that stiffness and it follows a different curve. If I zoom in on this, you can see that the results match initially, but for a very small load, it matches. As soon as your load gets big enough, then they really deviate from each other. All right, let's talk about material. This one's going to be a little quicker. But these are the three types. Let's talk about material nonlinearity next. And as far as this one goes, this basically just boils down to being able to include the stress strain curve information. Now you've probably, if you've used simulation for any extended time, you probably noticed this little SS next to some of your materials. No, that doesn't mean stainless steel. That SS is also next to some of the aluminums in our database. What it means is that there's a stress strain curve available to you. If you were to run a nonlinear study, you'd be able to access the stress strain curve and use that. So here is another animation example of showing using a stress strain curve and what it means for this wrench that I'm bending. The yield strength on this wrench is 90 KSI, and you can see I'm going to plot the results along this width here. You can see that I've got tension stress here, compressive stress there, and as I plot the results, as I increase the load, those tension stresses get higher and higher, the compression stresses also get lower and lower. And it's pretty predictable behavior, proportional behavior. It's linear until I hit the yield point on my material. This is where the material nonlinearity comes in, and now that some of that proportionality goes out the window. I increase the load a little bit, and this thing bends a lot more because of all the material yielding going on, until eventually it yields throughout the entire thickness and it snaps. Okay. So again, that boils down the three essential types of nonlinearity. Now let's go back here. We were talking. Well, the reason we were talking about that is to try to clarify what we mean by partially. How can something be partially linear versus nonlinear linear? So here's the summary here. If you run with Simulation Express, what kinds of nonlinearity can we take into account? It's purely linear study, none of them. Okay, but if you run with static analysis for assemblies, what can we do here? Well, we can account for some contact nonlinearity. For example, here, let me show you though. Let me show you there's some limitations to it. Let's look at this contact. And if you look carefully, you might notice something looks a little bit off. Right? Do you see it? The bottom beam is moving before the top one even touches it. How could that be? Well, what the static analysis is doing is it's running the simulation with contact nonlinearity turned on, but it doesn't save all the intermediate steps. It finds the correct final position of the two bodies for static equilibrium to be satisfied, but it doesn't show you all the steps in between it took to get there. So if you try to play back an animation, the animation just shows you going from the initial position to the final position, and it just interpolates between the two. So more or less, it works. The contact nonlinearity works, but if you really want to show like the animation leading up to it, you bump into some limitations. But what about for this kind of problem? This guy, and this is the one we're going to be looking at a little later on too. Does it work here? Yes, it finds the correct initial position and final position, but we kind of want to know some of the steps it took to get there. And you can kind of see the contact elements are a little bit off too. When you have very large displacements like this, and it tries to solve for those contacts, it can get a little hairy. So it kind of works for some applications here, but overall, depending on what you're really trying to do in this problem, it might not work. Okay. Now, so we can do contact nonlinearity in static analysis. What about geometric nonlinearity? Yeah, you can account for this somewhat. I think of this option here. You can turn on large displacement in the background. It's one of your study properties. By turning that option on, to me it's like you're enabling the Nonlinear Express solver. It's like a light version of a full-blown nonlinear analysis that'll incorporate geometric nonlinear at least. But if the solver fails, you don't have much recourse for troubleshooting it. It's basically if it fails, you can hit yes or no once or twice, and then it'll ultimately give you the last result it came up with. What about material nonlinearity? None of the above. Okay, cannot do any material nonlinearity in static analysis for assemblies. Now this is where full-blown nonlinear comes into the picture, where it can handle all three of these pretty well. If we look at the contact nonlinearity, those same two animations from before, they look more or less the way you'd expect. Okay, large displacements are accounted for. We do see the animations do show all those intermediate steps because we did solve for all those steps. Geometric nonlinearity, we account for that a lot better. We have a lot more options to be able to tune and fine-tune the solvers. Specifically geometric nonlinear options down here is 4 different options we can enable: large strain, update load direction, and so on, and also being able to tune the solver settings to make it easier to run these types of studies. And also the material nonlinearity, yes, we can account for that as well. We have all these different material models that you can incorporate. Okay. So with that, let's move on to a more specific example now. where we'll walk through these sort of four, I guess I shouldn't call them steps because it really depends on which level tool you have, but we're going to walk through 4 different ways we can sort of run the study with different assumptions, and we'll compare the results as well that we get between these studies. Now the ultimate objective of this study, if you take a look at the animation on the right, probably shows it the best. I want to try to figure out what is the insertion force required. How much force do I got to push on here to get this thing to begin sliding along there? So it's really the key part of this simulation I'm really interested in is just this initial part, that initial push right about to there. And it goes right there, okay? So I want to know how much force is required to do that. And I can use these different techniques in order to try to evaluate that. Now, first way we'll take a look at, though, is a quick hand calculation. Now, I'm not going to go into like the weeds on all this, but I do want to show a couple things where just having the SOLIDWORKS CAD engine in the background can really help with even doing things like hand calculations. So essentially what we'll do with a hand calculation, remember the goal is to determine the peak insertion force. So what this boils down to essentially is it's a bending beam problem. You can see if we just look at this top beam bending downward and upward and just assume some symmetry there. Really we just got to figure out how much force is required to bend this beam, and we might be able to figure out what necessarily would be the force of insertion. So as part of a hand calculation we can plug in numbers to an equation here. In this case, the important variables I do want to focus on with the SOLIDWORKS CAD environment is trying to figure out this length. Okay. Seems simple enough. I mean, what is just the length of this? And also this area moment of inertia. Okay, so these two terms. So here's the length of the load here I want to try to figure out using SOLIDWORKS, which you might think, oh, just take a measurement or something. Well, there's more to it than that. And then the cross section makes a big difference, whether or not it's an I-beam or a flat section. This will be the area moment of inertia, which I'll show. How do you have SOLIDWORKS tell you that? We've got our simple model here just to be able to look at this beam bending behavior. And maybe the first thing I'll do is let me figure out that moment of inertia, the cross section, see if this section is a good section or not. So I've got a configuration set that just chops the model down so I can see this section. And there's actually a tool in SOLIDWORKS you can use to evaluate this kind of thing. It's I wonder if you've ever used it. It's under here called Section Properties on the Evaluate tab here. If you click on Section Properties and then just click on this section, this face, and calculate, there it tells me. There's the moment of inertia around the principal moment of inertia around the X and around the Y, or you can look at it around the LZZ or something. But really the key value I'm going to use here is the principal around the X, 119.4, without me having to hand calculate out that number. So it's kind of nice. And then another thing about the length. You might think, where's the load? Where should my load be applied? Is it applied here at the very tip? That's not the right length, and it's important to get this length term correct because it's linked to the third. So if I'm off by a little bit, it's going to bring my errors way up. So if I put the load way out here, that's a little too far out. Versus I think the max load, the load will probably be right here when I hit that max force, somewhere in this ballpark. But how do I figure that out even? Well, you can use a little bit of the SOLIDWORKS sketcher to maybe help. You can draw things like a free body diagram in here. Here's my input force. I want to make that equal to the X component of where I think my contact force is going to be. And by dragging this around, I can see when does my input force peak out. Right there, it looks like. Okay, so and the short story here is, look how creative I gotta be just to figure out where that contact load's going to be. Okay, wouldn't it be nice if we could just have a tool that did this a little more directly? That's what we're going to get to with some of the other analysis types. But for now, I'll use whatever from here to the end. I'll use that as my length in my hand calculation. So here's what I came up with based on those metrics. Now there's some assumptions I had to make. For example, I'd assume that the contact location is based on the undeformed shape. That's a sketchy assumption potentially, but I don't know how else I could have did it. Maybe I'd pre-bend this thing a little bit and then use this free body diagram. Tricky. Also, I'm neglecting the deformation of the support in the female clip. That female clip's going to deform upward a little bit, and the support on the far left is going to deform a bit too. There might be some local deformations there I'm not accounting for with my hand calculation. And further, I'm assuming that the material's linear. We're going to see some of these assumptions vanish as I go to higher and higher levels of simulation. But let's move on. Okay. So by the way, the force I have here, I got when I did this hand calculation, I got 9.8 newtons is the peak load. Okay, but I'll put these up in a summary later, so you don't have to try to write them all down. So next, what I'd like to do is let's try to evaluate that peak force required using SimXpress. Okay, and all I'm going to do here is I'm just going to couple SimXpress with some of the elements of this hand calculation I did earlier. Instead of using this equation to figure out how stiff that beam is for bending, I'm going to use SimXpress to fill in that piece of information. I want to figure out the stiffness of the beam. So how do we do that? So here's essentially the same model, but this time I modeled in a surface where I can apply a load. I just want to test the vertical stiffness of the beam. I don't care about the lateral part of the load at all. It's not going to contribute much to the vertical stiffness. So what I'm going to do is I've cut the beam though to simulate where that contact point was based on that free body diagram I drew earlier. So there's still that assumption about that contact position. But I want to put a force here, bend this thing downward a bit, and measure the displacement so I know how stiff this beam is, and then plug that into a piece of that hand calculation and get a better estimate. So in order to run the SimXpress study, okay, I'll launch my Express tools, SimXpress. And this SimXpress is a really nice tool because it'll walk you through this wizard on my single body part, walk me through next to set up this study. So I'll go to the next step. Since I've already created one, of course, so I'll start over just to show you from scratch. And here I'll add a fixture, and you can kind of see I've sectioned my model down just to the essential regions, and I think I'll just fix these faces that I've split apart here. Okay, so it's got to fix somewhere, and we'll bend this thing downward. And then for the load, I'll put a force on this face that I put on the end here. And how big should I make the load? Maybe I should make it like that 8.9 from before, or really, I'm just going to make it 1 Newton. That way I can figure out the stiffness and plug that into my hand calculation. So I'll just do 1 Newton, the unit load. For my material, that's going to be, been making this thing out of plastic. So I'm going to do acrylic medium impact, okay, for the material in this case. Apply that. And assuming it's a linear material as well, we'll get to more of that a little bit more in a bit. And then finally, I'm going to go ahead and run this simulation. I see the thing bending downward. Does the part deform as you expected? Yeah, it looks about right. And now I can look at those displacements. So when I apply 1 Newton, I get 0.1337 millimeters of displacement. So I can take that number, plug it right back in to my compliance number here for my hand calculation. I see that when I did my hand calculation originally with just the pure equation, I got this compliance. When I did SimXpress calculation, it's got more compliance, meaning it's a little softer, it's less stiff. Okay, a little less stiff. Okay, and maybe that makes sense considering now I'm accounting for some of the local deformations that happen near the support. Okay, and so we do get a smaller peak load required. So that's how you can use, kind of use just a hand calculation and SimXpress coupled with those two to get a good estimate, at least a starting level estimate on the force, the insertion force. Okay, let's take it up another notch. Okay. If we're able to run a static analysis on assemblies, what does that now give us the ability to do? Does that make this problem any easier? For one, we'll be able to see contact forces, and you can see a problem with the assumption I was making from earlier, that free body diagram I was using before. Well, actually the peak force happens up here, believe it or not. After this thing deforms a little bit, changes the angle of everything, it kind of throws off my free body diagram. So you can start to see a little bit of the error in my assumptions from before, and this is where that static analysis for assemblies can start to help. So here now I'm running a simulation on an assembly. And let's see how much better we can get an estimation of that insertion force using this method. If you have SimXpress of course is included with every seat of SOLIDWORKS, but not every seat has this add-in here. So you have to have SOLIDWORKS Premium or Simulation Standard and above to be able to activate this add-in. And once I activate the add-in, it'll turn on the simulation drop-down on the top, and you'll also see a simulation tab get added to my command manager. And now I can do assembly level static analysis with this tool. So I'll set up a new study. I'll put the same materials I used before on here, the acrylic medium impact. Okay, so nothing really changing there between what I did with the SimXpress study. But But now here I can do things like include, I can fix, first of all, let me fix over here. Fix this side, and I'll put a force on the other side. But I can also include things like symmetry. If I go into my advanced fixtures, I can include symmetry. This is not available in SimXpress. And I want to go through and select pretty much all the important side faces here. You don't have to grab every single one, really just the key ones. And these couple of bottom faces, probably the most important. And I know I'm missing a couple there, but that should do it. Keeps the model constrained to the symmetric plane. And then for the load, I'll apply a load over here. Now here's the tricky bit. It's like if I key in a load that I think is too big, like 20 newtons, then what's going to happen here is this thing's going to try to slide a big distance, and it's going to have something to stop on. I'm going to start with a small load initially, one that I think will work pretty well. Maybe just 2 newtons, just to kind of ease into it. And then we'll scale it up in a moment. Now finally, for the contact, I need to tell how these components interact with one another. I don't want them to be bonded, so I'm going to get rid of this bonded contact out of my connections folder. And instead we'll replace it with a sliding contact set, the no penetration. So that's what, now we're doing a little bit of a nonlinear contact in our static analysis. And I'll do that between these couple of surfaces here, because I don't plan on running this to where it goes all the way to the closed position. But just these couple of faces here to these few faces here. Alright, and that's pretty much it for the boundary conditions and the connections. And finally, if I go to my study properties, I can turn on large displacement, and this is going to account for the large amount of deformations that might occur when the thing bends downward a bit. It might be a little bit more of a large displacement class of problem. Finally, I'll change the solver too. I recommend for nonlinear problems, usually use the Intel Direct Sparse solver. Okay. One last thing I'll do is I'll apply a mesh control just to refine the mesh in some of these local regions. Okay, just the regions where I have this contact primarily. It also is a good idea for me to refine the mesh over here where this beam's going to be bending a lot. But just to save on some time here, I'll keep this mesh pretty coarse. Kind of round it off here a bit. Okay. Finally, I'll use just a generally coarse mesh on everything else. You see I get about 2 elements through the thickness. This probably isn't good enough. I probably do want to refine it a bit more, especially in this region, but like I said, I just want a quick run time for now just to give you an initial idea of how this type of study works. So now I'm running large displacement and very quick to run. I get a result. Let's take a look at the stresses, for example. You can kind of see the stress region developing here. Now that tells me, what this tells me is that 2 newtons is not enough to get this thing inserted. We need more than that. So here's where you start to see some of the limitations of static analysis. Okay, well, what if I bump it up to 5 newtons then? Okay. Is that going to be enough to get it inserted? So again, large displacement solver kicks off, and you can see it's taking this in steps. Okay, across the top, it's saying, okay, now here's where I start to get some warnings. Solver experienced a sudden loss of contact. Would you like to restart? Oh, maybe. So it's kind of it's backtracking now, okay, and now it says it failed after 5 trials. Okay, once your loads get big, reasonably large, that's where things can get a little bit hairy when you try to run large displacement solutions. Now I can get this to run with a little bit of troubleshooting. I can get it to run. I can kind of force it to run, but I don't have a lot of options for troubleshooting to get it to work. Question, look like, did you get it there? Yep, great. Oh yeah, the reason I had to delete that contact though is because I did have a region down here that might have got bonded. I think I modeled a gap in there now though. Yeah, yep. Okay, good. Alright, so you can kind of see it starts to fail to run when I make that load a little too big, but there's some tweaks I can make to get it to work for stability. Things like turning on the use soft springs to stabilize model can help. Also modeling in additional surfaces that can collide with. But I just want to show you here though, I can get it to run at say 10 newtons. And here's what the result looks like when I apply 10 newtons after a little bit of troubleshooting and for a static analysis. You can start to see where that position is going to be. I can get it to run at 11 newtons. Okay, it worked. I can get it to run at 12 newtons. Okay, so 12 newtons still isn't enough to get it inserted according to my static study. Okay, what happens at 13 newtons though? Okay, it actually fails to run, and the large displacement solver backtracks, and it underreports the displacements. If I look at the graph here, you can see this underreporting as I increase the load. Here's where it's successful in running it, and then you can see the unpredictable behavior happening here, where the solver starts to fail, and it just reports the last step it was able to solve for. Okay, so according to my static study, it seems like 12 newtons is closer to the peak force, not like the 9 newtons we had before. Matter of fact, I can narrow it down even further to right around 12.3. Looking at this graph, 12.3 newtons, and then it starts failing. So to summarize, I know it was quite a bit to take in there. To summarize, if you do this using static for assemblies, you may have to do it iteratively, manual iterations, using the design study. I mean, the design study will help automate some of those manual iterations for you, but you'll still have to tell it to run each one of these studies from the beginning to try to see when is the point where it starts to fail. Okay? And right around that 12 newton mark, 12.3 newtons, if I run a finer study. Okay? That's when it starts to fail, because the model just starts sliding across uncontrollably whenever I apply even larger loads. And the stack for assemblies just can't account for that degree of sliding. But finally, what we'll do is we'll take a look at the nonlinear study, where we'll run this more directly. So here, what we'll be able to get out of this nonlinear study is a peak force and a whole curve leading up to that peak force. Rather than having to plot each data point manually, it'll provide that within one study, and I'll be able to see it as it's sliding along with maybe some friction enabled. You can even see some of that behavior. So to show this type of study, it's going to be very similar to the static study I ran a moment ago. Okay, have a lot of the same kind of inputs. But for this type of study, I'll set up a new nonlinear study for a moment, just to show you a couple of the key additional items. In one item I'd like to include, since this is a full-blown nonlinear study, I can, when I apply my material, I can incorporate material nonlinearity into this study. I've already got a material set up that has a what we call a tangent modulus, okay, and a yield strength, and that tells it to soften up. Once it goes over 45 megapascals of stress, that material is going to get a little bit more flexible. Okay, so it follows a more exotic stress-strain relation, which are things like plastics, rubbers. They tend to follow more than typical steel and aluminum. So if you're dealing with exotic materials, you may need to incorporate material nonlinearity into the solve. And then the connections, those are going to be pretty much identical to what I did before, and the fixtures will be pretty much identical. So I can go ahead and copy those over from a study I did before, but there'll be one thing I'll change about the way I load this that I want to show you. Okay, so let me show you the way I'm going to do the loading this time instead. Let me delete this one because it'll create it from scratch. So for a nonlinear study, a lot of times it makes more sense to apply your loads more like a displacement, prescribe a displacement instead of putting a force on there. So in this case, I'm going to do an advanced fixture where I'll be able to select this end face here and prescribe a couple inches or a couple millimeters or something of displacement. I'll do 0.5 inches of displacement to this, and that's enough just to get this thing carried right into this region here, okay, to a full insertion. So I can set this up to do just a 0.5 inch displacement, and then see what the results of that are going to be. Now let me go ahead and just fast forward to the results, because this study does take a while to run. I think last time I ran this one, it was about 20 minutes, 30 minutes. Okay, it's because I went with a quite a bit finer mesh than I did in those other studies, and I'm accounting for material nonlinearity as well. But with this, I can generate a sort of full-blown animation of the results. See like the stresses along the way, how they're growing, okay, rather than trying to generate animation manually with a bunch of individual static studies. Okay, so now it'll play back. So you see the insertion, and I've been showing you animations of the full thing going in and out, but it takes a little bit, obviously, longer to run that. And then also the key result I want to look at though is using this list result force tool. I can grab this end face, update, and we can look at a response graph, see what that see what those overall forces look like. Okay. So as we push this thing further and further, that's what the time represents down here, is how far I'm moving it. As I pushed it more and more, the load went up. It peaked out right about here, and I'm reading down here what the numbers are. It peaked out at about 0.169 seconds, whatever that means, but it actually peaked out at about 12 newtons, in the ballpark of 12, just a little shy of 12 newtons. Okay, and I can see, I can even look at that point. Where does it peak out? 0.169 it says. So if I go and edit my stress plot and look at what happens at 0.69 seconds, here's when it peaked out here. That's when the load is at its maximum. And then it actually gets easier to push once we get past this point, according to that graph. Alright, so to summarize then, here were the results from the different studies and the assumptions that were needed in order to run each. So starting with the hand calculation, I had to assume a contact location, neglect local deformations in the fixture, and also assume linear material. I got a result of 9.8 newtons. Okay. SimXpress, I got rid of one of those assumptions. I included some local deformations, and you saw the insertion force went down a little bit just by including some of the local deformations of this wall here. This region here probably made that big of a difference. Then I got rid of another assumption. The contact location assumption went away when I ran it as a static analysis for assemblies, and because of that the load went up by quite a bit. That's because, remember, that contact force was actually a lot higher, and that created an even bigger contact force, requiring even more load to assemble this thing. So a pretty big amount of error there. You know, they're both in the ballpark of like 10 newtons, but that's like 30% off. And then finally, I ran it as a full-blown nonlinear simulation with material nonlinearity included, where we can get more nice-looking animations out of it and troubleshoot the solver a little more easily. And by including that material nonlinearity, a little bit of give in the material, we saw that that load actually went down a little bit, but not by a huge amount. Now, there is a level sort of above these levels as well, and this is something you can check out some of our other webinars. I know one of our colleagues, Rune, did a webinar, I think last week, on this tool called SimiliaWorks. It's basically Abacus for SolidWorks. So check it out. You can do a very high-level nonlinear analysis with this tool, okay, even above and beyond some of the analysis capabilities we have directly in SolidWorks Simulation. Also, for further training, if you'd like to learn more about these topics, there we have a 4-day bundle simulations that covers the simulation essential basics and 1 day of Sim Pro, so the vibration and thermal side of it as well. And then a separate 2-day class that gets into the nonlinear studies, okay, in a lot more detail, as well as some other classes for vibration and composites.